In this video we'll see thermal cases. You see the conduction heat transfer through composite material, which have given different thermal conductivity, which are laminated material, which is A, B, C, and there are four materials with different thermal conductivity. One is exposed to high temperatures, 370 degrees C, and the other end will 66 degrees Celsius. So how the temperatures looks like through the length through three composite material along ADC and ABC, how it looks like within Abaqus. So you'll see this in detail, and finally graphically we'll compare the temperature along the distance different material. Sorry. So here we'll model the part, a 3D model. Let's begin. Start is creating a workpiece material. This workpiece is approximate size equal to, we'll change first we'll change this centimeter dimension into meter, because we have given thermal conductivity of 1 watt per meter per degree C. So I have to change this centimeter into meter. So we select the approximate size as 1, and we 3D model the formula and we solve part to can put in this way, and put the geometry, set the dimension, as the dimension here. How the area is given 0.1 meter square. So how the dimensions under root 0.01, which is around 0.31623, can say. It's like this, and extrude in depth 0.31623, this amount. So here we make a partition here, select this face, sketch a horizontal line and give a horizontal a vertical line, and then a horizontal dimension. So this dimension is 0.025 in meter, 0.025. Select this partition cell, select edge, extrude along direction, and then click the partition. So in the same way, sketch on this face, and sketch a line which is 0.05 horizontal distance from this side, 0.05. Perfect. Okay. So create a partition. Along direction, so here in the same way you select this middle face, select the right edge, the midway, we divide this part into two, and create partition. Okay, then we create a material with thermal conductivity of material A have 150 thermal conductivity. You can say material A here, the name. Okay, create material B, thermal conductivity of 30. Okay, and C, thermal conductivity is 50. And finally material D is material A, thermal conductivity of 70. Okay, then create section A, material A. Okay, section B, solid homogeneous, and materials B. Section C, like previous one, solid homogeneous. Finally section D, and put the material D. Then assign the material, click here, then select this partition, this material A, section A. So this automatically changes to green. When you assign a material, this geometry will change to green. So likewise we select this one, this is B, section B. Okay, this one, section C, and this one is section D. Okay, so we create instance. Okay, so you can see here visualization in material vision. We have different materials. Automatically choose different colors because we have different material. We assign different materials. So next step, we create step. This step must be heat transfer in procedure type, heat transfer. Continue and put this time period as much as this, and we select this one, steady state. Incrementation you can put 100, and you can increase maximum number of increments up to this. Okay, in this case field output request is by default is given, but a history output request you have to create in step 12. So in thermal category we select a time integrated HFL or any type. It's up to you. It depends on your requirement. You can choose one of the category. So here we go to load go to load, create here a boundary condition. In initial step, category other is temperature. Select temperature, continue, and select top face, all top face, and this side face as well as this 3 bottom face. Okay, then we modify this step category, say modify 66 degrees magnitude, as we have given this much temperature in one side. The other side will put temperature in initial step, then later will modify. First we create in initial step and later we modify the magnitude. So here, okay, and we modify the magnitude. We have maximum temperature of 370 degrees C. Like this, you put in this way. So in this predefined field, you can choose initial, other, and temperature. You continue and select set. We create a set previously, so this set, rate okay, and the initial magnitude is 66 degrees C. In the same way, we create predefined field 2 in initial step and select this set 2. We put 370 degrees C. Okay, so and I'll go to mesh. In mesh size, we determine the size. I select here in parts object. We determine this approximate size. This very rough coarse mesh, so you can increase by lowering this global size. You can refine a mesh like 0.0625 by dividing by 4. We put this one, okay, fine, is okay. Then we select this material type. The material type should be in heat transfer. In family will be, you select here heat transfer, and the material type will be an 8-noded linear heat transfer brake. That's okay. Then mesh, yes. So I have this mesh. And finally save this, or create job heat transfer. In parallelization, you can increase multiple processors to speed up the processing time and finish within a short period of time. So let's save, let's set a work directory. Let's see, in this folder heat transfer, and save as heat transfer. Let's overwrite. And submit job, submit and wait for result. Result is completed. So job is completed. So here go to result and see how the temperatures is looks like through this materials. You see from the top and bottom side, it have different temperature contour. Physically you can observe how the difference looks like, but graphically you can compare graphically by creating a path along the direction. We create a path along this direction. Let's put in this position. So we select a path around here. Select properly each node to get a good result, a smooth graphical representation. You have to select each node. Okay, so here path 1, we create XY data through path. Select path, then in this direction path 1, and then plot. So the temperatures looks like from one side to the other end, how the temperature is down. So it copy this value, and finally we'll compare with other side. Copy this one is since the path, what the path is, the path in this bottom direction, that means ADC, in ADC direction. It is ADC, and create another path which crosses through ABC. Then finally we'll compare the result. So create path like previous one. Select properly each node so as to get a good comparison for the bottom and the upper parts. Okay, so path is created. Then create XY data plot. Select path. In this option is must select, don't forget this one, path 2, and plot the result. So the results look like this. Then copy this result and plot these two data together, so easily you can compare. So this one is ABC material. So we plot result here, create data graph, select data, add data, ABC here, and x value is the same because equal distance. You can select either of the two, this one or this one. You can select that like this. Let's select XY data. Is x value select from the top to bottom. let's y data is this for ABC can, this one is y data and x along the direction, select this one. Okay, then add another can say, give the name ADC, the previous one is ABC. X value is the same, can select this one, and y value for ADC material we select like this. Okay, so how the graph tells us, if you see this graph, this the value, let's put legend, can put ADC D is they have a higher conductivity than B. That is why ADC is higher temperature around here. So this all about how the temperature conductivity through this composite material. This is all about today's video. If you like, can subscribe, share, and comment the video. Thank you for watching.